Potential Difference Research Lab. We're introducing the electric vehicle regenerative acceleration technology in this video. The EV regenerative acceleration innovation allows electric vehicles to recharge themselves as they drive, and in regenerative acceleration mode above 30 kilometers an hour, and in regenerative acceleration mode when electric power is sent to the EV's batteries, the regenerative acceleration innovation accelerates the EV above 30 kilometers an hour. And the more power sent to the EV's batteries, the more the EV is accelerated. And below 30 kilometers an hour, when below 30 kilometers an hour, the EV regenerative acceleration innovation operates as a conventional EV regenerative braking system and decelerates the EV while it's recharging the batteries. So we'll move up and we'll get a closer look at the current going to the battery. So I'm going to bring the system up to 30 kilometers an hour. Right now everything's in motor mode. So I'm going to bring it up to 30 kilometers an hour, and then it's set with cruise control, and then I will engage the three regenerative acceleration coils that are in the prototype into regenerative acceleration mode, and we'll be able to observe the current that's being delivered to the battery. And the more current we deliver each time we engage a coil, the more the speed of the system will increase. So let's take it up to 30 kilometers an hour. So the regenerative acceleration, the EV regenerative acceleration innovation allows electric vehicles to begin recharging their own batteries beginning at 30 kilometers an hour, and the more power that's sent to the batteries in regenerative acceleration mode, the more the batteries are recharged. The faster the EV, the more the EV is accelerated, and the less plug-in recharging is required. When the EV is operating below 30 kilometers an hour, the regenerative acceleration innovation operates like any other conventional regenerative braking system and decelerates the EV when recharging the batteries. The next phase of development for the regenerative acceleration innovation is to integrate it into a hub motor, as you see here, and for the regenerative acceleration innovation to be fully integrated into an electric vehicle as a traction motor, which allows for regenerative acceleration above 30 kilometers an hour and regenerative braking below 30 kilometers an hour. Thank you for taking the time to watch this video. Cheers.
So for every one time that this gear rotates, this gear here will rotate 243 times. So you can see if I move this one, you can see it's already, look how fast it's moving, and you can barely see that I'm moving the other gear. It also takes almost no force to stop it on this end, but a ton of force to stop or start the rotation on this end.
Hi, I'm Oscar van Deventer, and this is extreme reduction. It is a reduction that's very compact, and it reduces 1 by 11 million. And yes, you hear that right, 1 by 11 million, even though it's as compact as this. So let me explain to you how this works. In another video I've shown you the grinder gears, which is a mechanism where you have already quite a reduction. I'm turning the yellow gear inside the yellow gear. For each turn of my finger, the yellow gear skips a tooth, and for each circle that it goes all the way around, the green and the red gear have skipped a tooth compared to each other. So this is a mechanism that already provides a lot of reduction, and in the extreme reduction I have concatenated two of these mechanisms and to take the difference of them. So it's a bit complicated to explain, which is why I made this picture. What you see is a crank. Then we have a first reduction ratio with planetary gears in the yellow ring, which then, or in the dark blue ring, which then drives the green ring. And this reduction itself, it is 1 to something like 17,000, so that's already quite a lot. And then the next stage makes the same reduction, but in the other way around. And so the green one is moving forward and the red one is moving backward, almost at the same speed that the green one is moving forward, and the net effect is the 1 to 11 million gearing ratio. So I'll show you a bit how it turns, then I'll explain a bit more about the gearing ratios, and well, we'll see from there. So let me first show you the turning. When I turn one side, you see the blue gear pivoting inside the blue frame, and at the other side we have something similar with actually pink gears. And of course you see after all my turns, you see absolutely nothing has moved, and that's because, well, they are going at such extreme low gearing ratios. So I'll explain first to you the numbers of the gearing ratio, and what you see here is the calculation, and of course you can figure out this yourself at home. But first of all, in this calculation, it's the bottom part that's important. Here we have 26 times 26 minus 25 times 27. These are actually the gears of the tooth numbers of the grinder gears, so that are these. And this difference is exactly 1. Here we have a similar calculation, but then with one lower, 25 times 25 minus 24 times 26, also 1. And when you make this calculation as a whole, then you have 675 minus 674, which is also 1. So everything is nicely subtracted such that you get a very low number at the bottom, whereas at the top, if you multiply all of them, you get the number of 11 million, or to be precise, 11,373,067. So quite an extreme reduction. So in order to give you at least a feeling of that things are moving, I'm going to spin the inner axis a lot of times, and hopefully after a lot of turning you will see that things have moved. So let's get started. So what you have seen me doing is a couple of 100 moves, and when you look at the top, you see that the green gear has actually moved a fraction of a degree compared to the yellow gear. Well, when you can do the math, it's 1 to 17,000 something. So if I turn a few hundred moves, then of course the green one is going to turn a visible bit. And what you can also see is that the red ring has moved in the opposite direction compared to the green. And of course, with the total gearing ratio of 1 to 11 million something, you still cannot see that the red has moved compared to the yellow. And actually you have to believe the mathematics or turn even more and more to get this, to make it actually visible. So what's special about this is of course that it's an extreme gearing reduction. It is 1 to 11 million something, and it's very compact. You see it fits in my hand. If I would do the same thing with worm wheels and same size of gears, the thing would be much bigger. So we have a very, very compact, very extreme gearing ratio. And of course you can already guess my question, because well, it's nice to have this as a proof of concept, but what use does it have? So my question is, what is a practical application of a gearing ratio of 1 to 11 million that is this compact? Thank you for watching.
welcome back everyone. Today we're going to be talking about TEC stacking or cascading, and we're also going to talk about parallel TECs. So the pictures we have here are of some stacked TECs, and we're going to talk about what kind of impact that has on the device as a whole, and then we're going to compare that to TECs in parallel. So cascaded TECs are essentially TECs physically placed on top of each other, and you can buy them and they generally look something like this. Now you can just do this manually with your own TECs. You don't need to buy one that is cascaded or stacked, but they do make them. Now you will notice that when you look at the specifications of them, they will all move a very small amount of power generally, and that the delta, which is the maximum difference between the two sides of this thing here, between here and here, is greater than the delta from here to here, which kind of makes sense because this TEC is cooling this TEC. However, you won't end up with a delta twice as much. So normally you're going to get a delta of about 60 to 70 degrees per each layer for one of these, about 60 to 70 degrees. But when you put two on top of each other, or one on top of each other, you can obviously stack more than two, the delta does not become twice as much, and that is because, as I explained in the first episode in this series, the delta, the maximum difference between the two sides, is achieved when no heat is being transferred. Now when you have TECs that are stacked, that's not actually possible. That's because while this layer here might have a 60 degree delta, it will be using, I don't know, let's make up something, 50 watts. Now that means this layer down here is not moving nothing when this layer is moving nothing. It's now moving the 50 watts. So the delta across the second stage, I'm assuming that your load is getting applied to this, is the maximum it can achieve is reduced because it's always moving 50 watts of electricity when it's actually doing nothing. TECs that are in parallel are essentially TECs that you just put next to each other physically, and the effect on that is that's just essentially the same as having a greater Qmax. So if this has got 100 Qmax and this has got 100 Qmax, that's supposed to be max, then the combined total is 200. However, in this situation, the Qmax will be less than the combined total of each stage because they're obviously on the top of each other, so the second one has to move all of the heat applied to the top one plus all of the electricity the top stage moves. And that is why you will normally find that the top layer is less powerful, and you'll commonly see them stacked like this where they're reducing. If you find them like that, they'll generally be extremely gutless TECs, and this one is a completely gutless one. I mean, it's actually relying on the conductivity of the ceramic plates to the modules out here, which is not the world's greatest conductor of heat, but these, I think this one's only 13 watts total, this whole module, because this one here is 50 watts, and it's got a more logical path to transfer the heat from the top couples to the bottom stack of couples. So let's have a look at some of those examples with the calculator. So we're going to start with parallel TECs. Now this calculator already actually has an option for multiple TECs. I think we're going to stick with just one, and we'll use each calculator to pretend that it is each of the TECs. So for a start, let's assume we've got 200 watts and we've got one TEC. So this one's not there. And we can see that we achieve a 33 degree delta. We're using almost 800 watts of power. Now if we went to two parallel TECs, or TECs next to each other, we can compare that. So that would be the same heat load shared across two TECs, which is now half, and this would be the result. Pretty logical. However, you'll find that that is not the same as one TEC moving all of the load. I'll just fire up another one. You'll see that it's actually not the same. Turn that into 2. Right. So we've now got, this one's got 2 TECs, this one's got 1, and you can see that the watts moved is the same, but the power used is significantly higher on 2 TECs than 1. However, we are getting a better delta. So it really does depend on when's the best to use it. Now if we were to crank this up to say 400 watts, we can move that quite a lot. Now let's have a look. Right, with 400 watts, which is pretty close to its maximum for a single TEC, we're using nearly 900 watts of electricity, and we're only achieving a 3 degree delta, which makes this pretty pointless. But with twice as many TECs, or 800 Qmax, we can still achieve a 32 degree delta, which is a good thing. We are, however, using an awful lot of electricity. But that's just the example of one TEC versus 2 TECs. It's effectively increasing the Qmax. When would you want to do it? If you are unable to get enough physical Qmax with one TEC, why not have multiple ones? Now, I realize that we've got this input voltage at 100%, and you would normally not run it at 100%, and the idea would be to go to multiple TECs and run them at a lower input voltage to increase the efficiency. And we'll talk about that now. So let's go back to our 200 watts, and we achieved a 32 degree delta. If we go back to 200 here, okay, we've got a 47 degree delta, but we're using twice as much power. Now let's say we only wanted a 32 degree delta. We could reduce the power greatly. I don't know, let's try 70. That's still more. That's still more. That's not enough. Okay, that's a good example. Now we see the difference, and this is where it gets used. Where when we only had 400 watts of Qmax, to move our 200 watts of heat, we had to run it at 100%, and it used an awful lot of electricity. Now to achieve the same delta, we were able to use two TECs, run them at 52% to achieve virtually the same delta, but we have used roughly half as much power. And that means that you'll have to dissipate half as much heat to the environment, and that means that the system will be significantly better performing. You'll achieve an actual better delta because the thermal resistance of your copper, the water, your radiators will be only transferring half as much power. Well, it actually won't, but roughly half as much power. So therefore you will lose less of the delta to thermal resistance losses. So that's parallel TECs. Normally the idea is you want to increase the Qmax so you can decrease the input voltage so you can increase its efficiency, and we can see that here and here. And this is pretty much, well, this one, 2 TECs is pretty much twice as efficient as a single one. Good news. So let's go back to TEC stacking. Okay. So we're going to move them something like this. We'll go back to 1. And so this indicates one TEC on top of the other one. So let's have a look at what will happen now. Okay, so we have first stage trying to move 200 watts. And it is moving 200 watts. It's using 800 watts of electricity, and therefore the heat load is just under 1000. Now we go to the second stage and we try and cool the first stage, and we will be trying to move 1000 watts. And we'll try and calculate that, and it will scream, "I don't think so, Tim," because the maximum it can move is only 400 watts. So you need to, well, I mean, obviously that's not going to work. So what can we do? Well, we can reduce the power of each one of them to something like that. Alright, so now we're moving 200 watts. The electricity used is 155, and we've got a delta of 12 degrees, and we've got a heat load of 355. I think that'll work. So now we can put in 355, and that will work. So this, whatever this one's outputting, then moving, and we can work out the delta. So the delta would be the combined total of two of these. So the delta is going to be, what's that going to be? 21-ish degrees, while consuming 800 watts over here and 155 watts over here, 900 watts. Now that is certainly quite a lot. And if we just compare that to a single one, we can achieve a better delta for less energy used, or electricity, than we can with 2 stacking. Now you can change all these numbers around and jimmy around. You really shouldn't be running this at 100%, but you can see that stacking doesn't always work out. Well, actually, generally speaking, if you have a high Qmax, which if you're talking about computers and single 62mm TECs, it pretty much doesn't normally work out that stacking will actually help, or certainly not at full load. Yes, stacking TECs can result in an increase in delta, but it has the impact of reducing the maximum Qmax. which is counterproductive when we're limited to a relatively small Qmax of 400 relative to our load of 200. But something you can certainly play with and experiment with. Lots of fun can be had, especially firing up the calculator and moving all the numbers around to see if you can get it to work. There's absolutely no reason why, of course, you can't have 3 stages to the stack or the cascade. There's no reason why you can't have a TECs in parallel and a stack, and I believe if you have a large number of TECs in parallel and then stack to have, you know, thousands of Qmax, raw Qmax, and a number of stages, if you can run these TECs at a highly efficient or high co-op and move a small amount of energy because they're all in parallel, and then you can really see the benefits of stacking. However, you have to have a water chiller, and it would actually cost an awful lot of money in TECs, but it would be interesting to see if someone actually did test it out. So hopefully you've enjoyed that. So hopefully that makes sense. Parallel TECs is essentially just increasing the Qmax and the Imax. In TECs, stacking is a lot more complicated. Essentially, you don't get, the important things are, you don't get twice the delta if you put 2 TECs on top of each other, and it results in a reduction in Qmax, which is generally not a good thing if you're talking about a large load and a very small Qmax. It's fine if you have unlimited space in a chiller, but if you're talking about direct dying block, then maybe not. So I hope you guys have enjoyed that. I hope that made sense. I hope it helped, and I'm hoping we're all learning things together so that we can make water blocks, chillers, fridges, Coke coolers more effectively, and do it once and do it right if we understand how all this stuff works. Well, I shall see you on the next one, guys. Bye bye.
Guys, this is just moving on from the film canisters. I've decided to upgrade to the ice tray Mark II. What I've done there is just put in 10-cent pieces, copper 10-cent pieces, zinc galvanized iron. I've got tiny little neodymium magnets there to act as a link, a bridge there instead of a wire. I don't like using wires much. So it goes all the way around, comes back to here, copper positive and zinc negative. And I'm getting about 12 volts out of this baby. See there, oh, it's up to 14 volts now, and that's just from putting them in series, salt water, followed on top by equal parts spirit of salt and vinegar, watered down of course both of those before they're mixed. And that's nothing surprising to me. I expected to get about 12 volts out of that. I'm getting 14, but what really I was interested in was raising the amperage, and that's done through adding the spirit of salt and the vinegar, it seems. And now, where I was pushing about 0.2 of a milliamp, now I'm getting 2.5, or say 2. It slowly drops there, you can see it dropping down. Now, that is what I was after. I just wanted to raise that milliamps, because the amps are where all the work's done. That's where the current is, and you can see the result there is pretty impressive. That's a LED light running off earth and a solution, and it's a natural solution. It's not bad. Not bad at all. Implement series. Now again, you remember the last video that I showed you with the little mini cell, which I've got here. Now this was a little mini cell I used, made of just straws cut off at the end with bits of tissue in it and vinegar. And also I've got copper and zinc in there as well. And this little baby there was punching out about 6 or 7 volts, or whatever. And there's no reason that I have to have such large cells here. I'm going to test going down with a smaller cell and see if I can't produce the same amount of power, small volume of dirt. And I showed you earlier in the video that the volume of dirt doesn't matter, I still get the same amount of volts out.
Okay folks, here it is, 135.4 volts. All I did is mixed the 4 ingredients with water, stuck it in the copper tube. I got a carbon rod in the center, and there it is right there. 135.6 volts. Now this is still wet and it's drying in the sun. So I don't know what's going to happen once this dries up, but I'm getting 135 volts. And if you notice, look on the voltmeter scale, it is voltage, it's reading DC volts. Get that. I can't believe it. I just can't believe it. With this, rather than the heat mixture that for the thing is borax, Epsom salts, no salt, and alum. And I got a half a cupful of each. Put it together, mixed it up real well, added water to it, and let it pour the mixture in here. You got a thick batter, and that's what happened. Take a look at this, 135.6 volts out of this. Fantastic, absolutely fantastic. I don't know what's going to be when it's dry, but the carbon rod is not touching the cylinder in any way, shape, or form. What's separating the two is that mixture that I just made. So I don't know what to make of this, folks. What do you think? I'm very excited about this, and that's all, folks. Give me
the sand battery. I built on a smaller scale last time. This is the biggest sand battery I've ever built. And I've got a voltage of 175.8 volts, which you can store in a capacitor or even a battery, which you can on a later stage use to produce electricity. This is actually the biggest scale. Just put sand inside and I made it a little bit wet so that I can produce electricity. I said last time I'm gonna build big, and I did.
Our product enables remote wireless detection of human vital signs without the subject's knowledge. While a terrorist may seem cool and composed on the outside, his involuntary response will give him away. In addition, live friendly soldiers can be found in dangerous areas without risking personnel for recon. Our system works by generating low-energy millimeter waves. They are able to penetrate through many common materials, including clothing and masonry, and efficiently reflect off optically rough surfaces, and yet they provide a high degree of sensitivity to minute displacements. As the wave reflects from the target, its phase is shifted proportionally to the movement of the target. The phase can be extracted, and the displacement of the target can be demodulated. When the system is aimed at a human's chest, we can see the chest's movement. There are components of chest motion due to heartbeats, breathing, and gross movement. Using signal processing, we eliminate noise and motions due to gross movement and analyze only those due to heartbeats and breathing. Since the antenna has to be well aimed at the subject's chest, We employ cameras to identify and track the subject, and a pan-tilt base to move the whole assembly for constant aiming. A color camera locks onto the subject's face, learns a hue histogram of the face, and performs mean shift tracking. At the same time, a depth camera segments the image based on the depth of the target so that only pixels at the right depth are considered for processing. The millimeter wave system itself can be seen here. First, and most importantly, is the millimeter wave sensor and antenna assembly, which is what gathers the in-phase and quadrature components of the signal and returns it to the computer for processing. This unique low-power, all-solid-state millimeter wave sensor itself can be battery operated. Then there are the cameras, which perform the real-time detection and tracking of a human subject and return the data to the pan and tilt base, which is what moves the entire assembly and follows the subject as he moves around and maintains the aim at his chest. In the following demonstration, the screen is split into 3 parts. In the top left is the system assembly, which shall be moving to follow the subject. In the top right is the subject as seen by the color tracking camera, where the oval and rectangle are the location and scale of his head, and the purple circle is the location the antenna is aiming. In the bottom half is the measure of displacement as it is being calculated by the computer in real time. The red circles represent calculated heartbeats. Also on the graph are the locations of heartbeats obtained from an ECG that was gathered simultaneously, shown in green. This is a ground truth used for verification and was not used at all in the algorithm. The sensor starts off aimed at the subject's chest. While he is seated, the subject holds his breath for a while in order to demonstrate that individual heartbeats are visible. As the subject stands up, the system follows his movement and maintains good aim. Now the subject demonstrates the fidelity of the system during lateral motion. Here the subject demonstrates the accuracy of the system during large gross movement. The subject's backward movement is larger than that due to heartbeat and respiration, as is evidenced by the scale of displacement on the bottom of the screen. Even with such large movements, the system continues to process the data with good accuracy. The system works on various body types such as males and females with larger and smaller frames and builds. Although our system is currently intended for homeland and national security applications, this novel technology has a wide range of applications for standoff monitoring of non-stationary targets, including home health care, collision avoidance, condition monitoring of operating machinery, and non-destructive evaluation.
Okay. I thought I would do one last YouTube video. Here's a common rock, and we've drilled the rock, and we've cemented. You can see here we've made a mixture, and we've put it in the rock. So we have this rock. See it? And we've made the electrodes. One's magnesium with a screw and one's copper. And there's your LED. And we're going to leave it there. And so we're at about 1.7 volts. You want to measure this. So I'll measure it for you. And I'm going to put this under load. And just leave it and test it. So this is where our voltage is. That's pretty flat, stable there. It's moving around just a little bit. So I figure it's a good experimental example of using a rock to do this. Because I don't want any wet at all, and believe me, it's not wet. So there you go. We're just going to leave it there. So I thought we would share this with you. And see what happens. And I'll report on the test results on this, on the group.
I'd like to show you an example of levitating small objects with sound waves. Let me just remind you how a loudspeaker works. It's just a diaphragm that repeatedly pushes on the air, producing high pressure waves that move away. And that's what we have here with this little gizmo. It does the same thing, except it's at a very high frequency, 28,000 hertz, which is way above our human hearing range. So these sound waves move upward, and up above I have a glass plate which is going to reflect the sound back down again. And when the distance between the glass plate and the loudspeaker is just right, then those sound waves that are moving down will interfere constructively with the sound waves coming up and give us regions of high pressure and low pressure which don't move around, they stay in one spot. And it's in those high pressure zones that I'm going to try to levitate a small ball. So let me turn on the power, and even though I can't hear it, I'm still going to use ear protection. As I said before, the distance between the reflector and the loudspeaker is just right. If I change it, and which I'm going to do, you'll see that this standing wave disappears and the balls are no longer suspended there. We've now set up the little loudspeaker and the reflector in front of this mirror, which is part of our Schlieren optic setup. And the purpose of that is to be able to actually see where there are regions of high pressure and low pressure in the air, especially the air between the reflector and the loudspeaker. So let me turn up the volume, and before I do that, I will put on my protective hearing. And if I adjust the height of the reflector, there's a point at which you see bands of white, light, and dark. This is the standing wave, and it only happens when the distance between the reflector and the speaker is some multiple of a half a wavelength. So every single one of those bands is a half a wavelength. If I go up a little higher, then it disappears again, but if I continue to go higher, then it will come back when I'm at another half a wavelength, a multiple of a half a wavelength away. Now, it's in these bands that I'm going to place the little balls. And you can see the little ball settles down where there's a bright band, and that is the high pressure area. And I know it's a high pressure because you see there's a white band right next to the reflector, which is where the highest pressure will be. If I again change the height, the standing wave goes away and the little balls will fall down.
Researchers have come up with a new 3D printing technology that makes objects appear all at once, seemingly from nowhere. The new approach is built on technology for pinpoint delivery of radiation in cancer patients. The researchers used a computer-controlled digital light projector to cast images through a rotating clear container holding a photosensitive gel. The projected images are based on a scan of a 3D object. As the container rotates, photons entering from different angles meet at select spots in the gel. Where they meet, their combined energy solidifies the gel. Where photons don't combine with enough energy, they pass on through without altering the material. The approach is fast, able to create complex objects, such as a centimeter-sized copy of the Thinker, in just minutes. It can also create 3D plastic parts around existing objects, such as a plastic handle around a metal screwdriver shaft. So while this device may not print Earl Grey tea hot on demand, it does induce some of the same sense of wonder.
.85 volts. The battery's drying up a little bit and the voltage is going down a bit. Still, all in all, I'm very pleased to see this. Here's a close-up of this. Very simple. Carbon tube cut off of a home water filter. You can make 3 of them because it's about 9 inches, those water filters. Cut them into 3-inch sections. Magnesium rod in the center. Screw on the top is brass. Screw in the shoulder of the carbon is brass. And that's what you get, folks. And let's see. Voltage. And this time it's true volts. It's not millivolts. So we're getting about 1.85. I don't know what the amp draw is on this yet. And I guess in time we'll find out. But I'm happy. Thanks for watching.
Crushing, aluminium crushing can, crushed with forces. It's still crushed, it didn't kill him crushed. I find it extremely peculiar. Then we have our Leyden jars, custom made, gunsmithing spec, military spec. Of course, these are, I have to be careful with this discharge. I discharged it before. Asymmetrical, bipolar wound, pancake coil. And here you can see we had to put our samples in the box to prevent them from flying about the room. You can see a wrench there. Bent, severely bent.
Here you see the levitation with the bent wrench. A lot of this technology comes from Los Alamos and Montauk. I worked with the CIA at Montauk in the 80s. We initially were working with very powerful radio antennas and noticed some strange effects when we fed them through a Maxwell accelerating capacitor bank. These are amplified when used in strong electrostatic bubble fields. The helix pancake asymmetrical bipolar coil works very well to localize this effect. Here we have the polar molecule of water being underneath. The silver becomes very soft within the sphere of the influence of this pancake coil. A lot of this technology is seen in flying saucers, Area 51. This looks harmless enough, but this is the same technology that the aliens traded the government for, and they've been using it. It was used in the Philadelphia experiment with Einstein and Brown, the Bradford effect, high voltage, first described when they were welding big plates. Edison, Tesla worked on the Philadelphia experiment as well as earthquake machine. The twisting of metal is commonly seen with those effects. Here we have what looks to be crushing and hovering back and forth in it's a pulsating field. Here's the aluminium working for the CIA, Los Alamos, Montauk, the underground tunnels, RF, radio. When they first discovered the time dilation, which resulted in parallel universes of which this is one, that's really where this technology came from. Discovered doing Kirlian hovering, the twisted Kirlian photography with the silver and electrostatic high voltage. some of these effects became apparent. Here's military-grade naval spec. Ball bearings doing some very strange stuff. This was a dielectric and constructed with stainless steel, neodymium, small capacitor-type motors for the hovering, peripheral corona loss. It's a plastic, non-conductive, being responding to the field, flux, gravity, morphing, modulating. Now, when the field is reversed, we can see the can being crushed by the additional gravities. We may do some more experiments with crushing of cans later. This was a new thing. We changed the polarity on the capacitor. And here we have a combination of high frequency and the sphere effect. This is silver or stainless steel, 301 grade stainless steel, rubberized and instantly transmuted. Droopy dog effect, igniting water. So we will have schematics shortly, information on the CIA underground tunnels, the reptilian bases, hollow earth, Hutchison effect, all for free, and levitation. Stay tuned.
I've seen levitation of steel ball bearings, glass, where they will levitate. Unbelievable. I've seen electricity go right into the objects and a million pieces just fly apart.
In fact, using only 75 watts of energy, enough for a small light bulb, Hutchison made a 60-pound cannonball rise off the table. It would also fuse dissimilar materials, heat metal but not burn the wood it sat on, shatter metal as well as change its crystalline structure. This was something to write home about.
Beginning of 1980, experimenting with all the electromagnetics and electrostatic equipments I had at the time, I started to notice some very, very unusual effects, such as a room being filled up very quickly with multicolored lights, steel bars sitting on wood and not causing any fires, metal turning to jelly, things levitating and jumping off to the ceiling, or simply go up, hover, and then fall back down.
Dubbed by some as the poltergeist machine, there is no one machine, just a lot of old Army surplus gear, randomly tuned by John. No one knows how it works. John has apparently figured out the right combination of radio waves and electrical energy to create the effect. If it could be proven, its impact would be huge. You'd have to rewrite most of the science textbooks, especially the part about... An example of this kind of random event happened in 1989 when a visiting Vancouver news crew was setting up at John's lab to film the Hutchison effect. The target area was that yellow crate with the metal objects. But to everyone's shock, a sponge in the back of the room took off into the air and then fell back down. John didn't actually see it and was genuinely surprised.
Like that, it went up and hit the ceiling 1 second, maybe 2 seconds, and then came down.
Kidding.
No.
Well, some time ago I was doing some testing and got into some big trouble after I levitated a toy UFO and some other objects.
Apparently, John's experiments were lifting objects in nearby homes, and the neighbors called the police.
The police came full bore in here with engineers, inspectors. They photographed all the equipments very carefully. It's almost like if you called in a cleaning crew. They didn't touch anything. It's like they made everything look neater for some strange reason.
It seems like someone in the shadows still cares what our hero is up to. Frustrated by authorities and lack of recognition, John has been spending time developing his new project, batteries that last forever, based on the somewhat bizarre zero-point energy theory. Followers of this theory believe that all physical matter floats in a sea of energy, which, if collected and converted into electrical power, could more than meet all the world's demand for energy.
I feel everything has a life force to it, because I tend to visualize that atoms are a whole universe, and when they're combining one atom to make millions, if not trillions of them, you have a piece of metal, perhaps. Every time you run your hand across a piece of metal, you're taking off several million atoms at a time.
To demonstrate how energy is everywhere, John uses rocks from his neighborhood and in 2 hours makes a 0-point battery strong enough to power a pen light.
I make sure it bonds. Almost 1/2 electron volt. This is better than a conventional battery simply because it never runs down. So with these things, they could last approximately as long as minerals last, up to maybe 1,000 years, unknown.
Realizing his batteries could help solve the world's energy crisis, the Japanese have embraced John and funded him to build his bigger crystal-based models.
I got orders from Japan and sponsorship for me to make more of them. So the money would come through into my bank account, and indeed I made units that are actually in Hiroshima City. You don't mind.
While various 0-point energy devices were funded by the Japanese, so far none have taken off on a mass scale.
John Hutchison is probably the very visual proponent of the whole kind of 0-point energy movement. 0-point energy devices could revolutionize the planet. If you can build a 0-point energy reactor about the size of your microwave oven, put it in the back of your house somewhere, you run your house. You don't need to, you run all its electricity needs. You don't need to pull anything off the national grid. Well, if you put that into the third world, you're going to revolutionize the third world. That is as much a threat to some people as it is a benefit.
And as far as the Hutchison effect goes, I'm rather disturbed that the U.S. government and aerospace corporations has it. The concerns of it being used for an evil force by the military-industrial complex disturbs me quite a bit. I like to see it used for the helping of nature, because there's so much pollution going on with nature. Mankind tends to want to fight each other all the time with wars, whereas Mother Nature rolls on with great energy and power.
It's absolutely essential for the world and survival of the world that we get off petrochemicals. Failure to do so, it really threatens our national survival.
What I like about John is that he doesn't compromise. He doesn't compromise his appearance. He doesn't compromise his lifestyle. What he does is pretty unconventional. So, you know, good on him. I'm all for that, and I wouldn't want him to change. He's fine just the way he is.
Whether building batteries or levitating objects, John Hutchison is an eccentric enigma. Of course, virtually no mainstream scientists take John or his invention seriously. But then only a little over 100 years ago, people believed it was impossible to send a radio wave across the Atlantic. Now just imagine if this backyard scientist really has discovered a primal force of nature that could transform our world.
I am only taken seriously by the military scientists. The academic scientists really don't know what to make of me. Well, to say a lot of other people too don't know what to make of me. I'm just a different person, and I'm kind of happy with myself. I don't want to try and change myself.
stationary hub from the rotating rim and wheel. Offsetting the motor from the center creates a torque multiplying effect, reducing the power needed to start and stop the wheel. The patented 3-pointed bearing spider reduces friction to 1/5 while doubling the structural strength of the wheel. Brake rotor weight is reduced by 60% and unsprung weight by 50%, enabling in-wheel motor installation without weight penalty. Orbis technology enables converting a 2-wheel drive into a 4-wheel drive without adding unsprung weight to the vehicle. We added a 31-pound, 50-horsepower Zero motorcycle brushless motor to each of the Honda Type R rear wheel assemblies, upgrading them from passive to independently powered wheels. Orbis designed custom parts to replace the factory wheel assembly and to remove excess weight for optimum operation and integration. All this became one bolt-on kit with ease of substitution. The Orbis assembly was tested for friction. The dynamic friction of the wheel with no load was a mere 4 watts. To get an idea of just how little this is, you can get as much as 10 watts of friction variance with a bicycle wheel and chain just by using different routes. This hybrid vehicle has multiple benefits in relation to a factory configuration. We achieved a 5 times reduction in static and dynamic friction, as well as a 30% increase in mechanical braking efficiency, due to a 30% decrease in brake temperatures. We created an all-wheel drive gas-electric hybrid Type R, which has 100 added horsepower with minimal increase in curb weight. We improved 0 to 60 times and increased torque by 40%, improved front-to-rear weight bias and fuel economy while reducing emissions. We improved safety and control via lighter wheels and reduced inertia, improved traction via all-wheel drive, and, to top it off, a reduction in brake fade. The completed hybrid vehicle was road tested in city and highway conditions using an infrared thermal camera to
So guys, here I believe that the capacitor bank is charged now. So let's touch the 2 wires over here and see if it creates a short circuit and a large spark. Okay, you see, on its shaft. Okay, like this. Let's touch the terminals of the DC motor to the capacitor and see some shaft movement. Whoa! So guys, here as you can see that I am using 2 aluminium foils and 1 cling wrap, and there is another blue cylinder like thing which I'm going to tell you afterwards what it is and why I am using it and how you can get it. So guys, this what you see is an old water purifier membrane. You see it's showing membrane element, it's discarded, and I wanted something to roll these 2 foils and cling wrap on. So I'm going to use these. You can also use a hollow PVC pipe for the same purpose. So anyways guys, the first step is to take the cling wrap roll and spread it. After that, take the first aluminum roll and spread it on the cling wrap roll, and then spread the third aluminum roll and place the set of cling and aluminum roll on it, and then place the membrane cylinder on it, and if you are using a PVC pipe then place that on it. Then also create sharp edge cutting of the aluminum and cling wrap set to prevent any contact between the aluminum sheets, because that can create a short circuit and damage the project. So guys, after completing the wrapping part of the aluminum foil around the membrane, I will tell you a very important part, which is that we always have to make sure that
the two aluminum sheets don't get in contact with each other electrically, because then it is going to create a short circuit and our capacitor is not going to work, and probably the power supply that you are going to use to charge the capacitor, that is also going to get destroyed. Now guys, before fully completing the rolling process of the aluminum sheets, you will also have to use two wires to give access to electrical connection to both the sheets, aluminum sheets, for using it as an electric capacitor, power capacitor. So guys, after stripping off the wire insulation comes the part of placement of the wires. So first take the red wire and place it on the top aluminum sheet by folding it to create double contact area between the sheet and the wire, and then simply roll it over. And after doing that, take the second wire, which is the green wire I'm using, and take the cling wrap and create a space between the lowest aluminum sheet and the cling wrap and insert the wire in between the empty space, and then roll it again. And after that, roll the sheets until the full 9-meter aluminum sheet is utilized for the project to create maximum area for better capacitance in this capacitor making project. Here, as you can see, that I've used this tape to keep the aluminum foil in place because the wrapping part finished over here, and these are the two wires that I took out from the membrane by creating the diagonal drilling. Okay, so with that being done, it is quite steady and rigid, obviously because it is just a foil wrapped around a membrane. You can also use a PVC pipe. Let's put it to test. So the first part of the test is the conductivity test, to make sure that there is no short circuit, which is a high probability. Here, as you can see, that I have pointed the meter knob to the resistance check mode, and here it is showing 0 ohms. So if there is going to be a short circuit, it is going to beep. So as you can see that there is a beeping sound, which indicates that there is a short circuit, which I have to rectify. So guys, after carrying out all the precautions and checking if there was a short circuit, I still tested and it beeped. Yeah, like this, and it continues to beep, which made me do more tests on real capacitors that we get pre-manufactured. Okay, then I tried this. As you can see, this is an AC motor capacitor, 68 microfarad, and if I connect the multimeter, see, it's not beeping over here, but it beeped initially. You see, it beeped, and now it stopped beeping. Okay, now when I reverse the terminals, then again it beeped and stopped beeping, which means that it is charging and discharging, something like that is happening in this AC capacitor. Okay, and the capacitance of this capacitor is much higher, because of which it is beeping a little longer. You see, it is beeping and beeping and beeping, which indicates that a capacitor beeps until it gets charged by the battery to the voltage that the battery provides. At least I think it's that, I'm not sure, but this is something really different, that it keeps on beeping. Like this one beeps, I think, because its capacitance is very high, like 41,000 microfarad. Okay, but this one beeps only for like 1 or 2 seconds and then it stops, because its capacitance is only 80 microfarad max, as I showed you. You see, it stops. So this made me think that there is no fault within this capacitor. Okay, yeah, I think now it is not beeping because maybe this one is also charged. So guys, I did one more test to make sure that a multimeter produces an output voltage at its pins when we do the resistance check. Okay, so for that I used 2 multimeters. One is already this one, and the second one is this one. So this multimeter, I have pointed it to 20 volts DC to confirm that if it produces some voltage, then this is going to display it. Okay, so these are the 2 pins that you see. These are from this multimeter, keeping it like this, and we have the 2 pins from this multimeter here, keeping it like this. Okay, so now if we touch the two pins, you see that it is actually producing some voltage that is being displayed over here to the multimeter. So this confirms that the capacitor was actually charging to that voltage, because of which it continued to beep. Okay, and once it would have gained that charge, then the beeping would have obviously stopped, just as in the case of this AC capacitor. Now guys, there is no insulation around this newly made capacitor, and the charge, when it charges, can get discharged from the air around it. So I have to like minimize that discharge. So for that I'm going to use this black insulation sheet. Okay, so guys, here as you can see that the capacitor bank, homemade capacitor bank, is completely ready now. Okay, and this is going to isolate the internal metal sheets from the air around it or moisture around it. Now this, what you see, is a power supply. Here you can see 32 volts DC and 5.6 amperes, which I'm going to use to charge this capacitor bank. Although this is an AC capacitor because it contains only 2 sheets and a cling wrap, but it is also going to charge on DC. So guys, here I believe that the capacitor bank is charged now. So let's conduct the short circuit test first. Okay, seems like it is charged. So let's touch the 2 wires over here and see if it creates a short circuit and a large spark. Okay, you see the capacitor is working. You can see that I'm touching and removing the terminals, because at the beginning the capacitor creates a short circuit, because of which the power supply turns off. So guys, as you can see that the lights have been turned off, and it's time to do the short circuit testing. Okay, now guys, this what you see is a 9 volts to 32 volts car headlamp bulb, night eye. Okay, it also has a BLDC fan at the back of it. Link to buy will be provided in the description, you can check it out. So I'm going to try and glow this bulb with this capacitor bank and see for how long can it hold the charge. Yeah, I think the charging is complete now. So let's touch the terminals to this night eye, but the voltage is just to its maximum, so there is a high probability, even if it is like 0.1 or 2 volts high, it is going to fuse. But let's see what happens. Okay, you see that it glowed for like 2 or 3 seconds and then it turned off. So guys, let's charge the capacitor once again in the reverse direction. This time I'm using black wire to the red and red wire to the green one. Charged by now. So now it's time to connect the terminals of this motor to this capacitor bank and see if it can run it. Okay, you see it is running and slowing down because the capacitor is now discharging. Well guys, this one what you see is a 36 volts 15 amperes DC motor, really big. Okay, so I'm going to try and run this 15 amperes high current motor with this capacitor, and let's see if it can start it for a few seconds or so. To make sure that we can realize that the shaft is moving from far off distance, I'm going to place this big clip on its shaft. Okay, like this. Seems like the capacitor bank must be charged by now. Let's touch the terminals of the DC motor to the capacitor and see some shaft movement. Whoa! Well, it was very dangerous. So guys, I hope you liked this video and learned a lot from it on how to make a capacitor at home from aluminum foil. So thanks for watching. Hit like and subscribe.
I thought we'd share this with everybody. Here's a series rock. The cells are made in series in the same rock. And the rock is basalt. And we're just going to let it sit here and see how long it will go. But it's basically what you got there, it's series. To test. Put the power oscillator on that. Grab that oscillator over there. There's the oscillator. The series rock. So you can do it in the same rock. And there you go.
You're looking at a 3D bioprinted lung-mimicking air sac that's able to pump air into airways, mimic blood flow, and was built using living cells. Granted, it's smaller than a penny, but this lung-mimicking air sac could bring us one step closer to understanding how we could replicate human organs using patient cells, which could one day help to avoid organ rejection. The team behind this model is trying to replicate the complicated architectural structures of our organs using 3D bioprinting and use the lung as their proof of concept.
It is a very complicated structure, yet it has extremely clear readouts for its function. If we have an image of lung tissue, we can pump in deoxygenated red blood cells. We can ventilate in the airway oxygen, and we can see to what extent those red blood cells will take up the oxygen that we've been putting into the aerosol.
Being able to print multiple independent vessel architectures has been one of the biggest challenges in the world of artificial organs. That's because our organs are, well, pretty complicated. You see, each tissue has its own knotted mess of blood vessels, which are physically and biochemically mixed. And they serve crucial purposes by supplying organs with essential nutrients. Take the liver, for example. It has over 500 functions, like producing bile for digestion and maintaining the right amounts of blood sugar within the body. All these functions depend on the intricate network of vessels to get their necessary nutrients. It's this multivascular architecture that makes mimicking and replicating human organs so difficult. So if we could figure it out, the payoff would be huge. Over 100,000 people are waiting for organs in the US, and bioprinting healthy organs could be a way to address this shortage by supplying replacement organs. It could also reduce the incidence of organ rejection, since bioprinted organs would contain the patient's own cells. But working with living cells is not easy. They're extremely fragile outside of the body, and once they've been extracted, they need to be placed into their final structure as quickly as possible to ensure survival. The cells are then encapsulated within a hydrogel, a water-based material which emulates a cell's environment to allow them to survive for longer periods. So how did Jordan and his team print the lung model? They used a technique called stereolithography apparatus for tissue engineering, or SLATE. It's an open source bioprinting technology that uses additive manufacturing to create soft hydrogels layer by layer by using light from a digital projector.
So this is a light-based polymerization system. So we have a light-sensitive liquid that when you shine the right color of light at the right intensity of energy, the right number of photons hit that sample, you can convert that liquid into a solid only in that region.
But using light also created some issues, since the light could get into previously solidified layers, thus disrupting the intended pattern. To address this, the team searched to find an element that could block light and that was biocompatible. And the winner was food dye.
These biocompatible food additives that all of us are eating all the time anyway, we already know that they're biocompatible, they're compatible with live cells, and they can be used as potent photoabsorbers to block the light penetrating previous layers, getting us our complex architecture.
The food dyes were able to confine the solidification to a thin layer, creating the desired internal structures. In the end, these tissues proved to be sturdy enough to withstand blood flow and pulsating breathing, the rhythm that mimics the pressures and frequencies of how we breathe. So this model may be tiny, but it's just the beginning for Jordan and his team. They plan to make more complex designs and scale them up. And in the spirit of teamwork and advancing research, they've made their work's source data freely available.
We're using open source to be able to make the 3D printer. We're giving back to the open source community our designs. But I think scientists in general get a little bit nervous about releasing things into the open because they're like, well, why do people really, what are people going to use this for? I don't really know. You actually want to open source your stuff because you don't know what people are going to use it for. And that's really the power behind open source, and it's really the power behind science.
And thanks to collaborative efforts like these, we'll one day be able to 3D bioprint organs to help address the organ shortage. If you like this video, check out our other 3D printing video where a new 3D printer can shape objects all at once using specialized synthetic resin and rays of light. Make sure to subscribe to Seeker, and thanks for watching.
All right, this is the test wide open with my little setup. Let's see what she'll do. That's about 50 volts. About 120. Okay, increase the hole diameter on this, and we're going to try it again wide open and see if this helps. Alright, here we go. That's about 120 volts.
Alright, today we're going to make a crystal battery. It's not something people talk about too often, but it is a pretty cool little, it's a little something, it's pretty cool the way you can get electricity. I'm going to show you how to make it, how I made it. I made some about 6 months ago and they still running non-stop, producing electricity. I have about 30 LED lights running off of them and they've been running non-stop for about 6 months. So I'm going to make one and show you. And show you how to wire it all up and everything. Alright, it goes by ports, and you know, they got people who made them, they last 10, 15 years and they still running, so it's a long run time to change up your measurements, but this is the measurement I use and it works pretty good. I'm gonna do about 1 port, or 2 ports. Epsom salt. You know, and I also found that you know, you don't have to go big, you can go pretty small and still get a pretty good voltage out of it. And 2 ports no salt substitute, which is salt silicon, I believe. I'm gonna do the same amount. 1, 2. Do alum, but you ain't gonna do as much, quite as much. Do about a quarter. Whatever measurement you use, do about a quarter of it. And there's regular salt. Plain salt, don't do the same thing, about a quarter. And that's pretty much it. Now they got all kind of people doing all kind of experiments, changing up the mixture, and so now everybody's trying to figure out a more efficient way. I need to turn it really, really low. You don't need a lot of heat. It's gonna melt it. You're basically gonna cook it down. And they basically getting the moisture out of it. And it don't take long. Like I said, a lot of people are changing up different kind of salt, adding different kind of things to it, and trying to get more of a bang for your buck. Because this right here will give you about 1.5 volts. It's pretty good with something small like that. There's 1.5 volts that lasts for years and years and years and years and years. So it's starting to melt to a big old paste. And you keep stirring and mixing, stirring and mixing, stirring and mixing. And some people, they cook it in different parts and mix it later. But like I said, I got a battery's been going on for about 6 months and they're doing good. Still putting out the same voltage. You see the stove's not very hot, it's just a very low heat. You see just that little bit of mixture, you can make a lot of small batteries with this. So it's been cooking for a while now. It's becoming like a creamy marshmallow texture. I'm just taking my spoon and smashing it down and stirring and mixing and smashing it down. Alright. Just gonna take a little bit in there. It might look hot, but it's not.
It's copper fitting.
Yeah, it's just a piece of copper. I'm gonna put my magnesium. Oh Lord. It's like I got hard on me quick. And it's very hot right now, but it's gonna cool off very fast and it's gonna get hard like concrete. It's gonna take about 30 minutes. Just trying to, once it starts setting, you don't want to fool with it because then it gets, you start cracking it. You don't want it to crack. It's gonna be airtight once it's all said and done.
It's a piece of magnesium rod.
Yeah, here's the company I ordered it from. It's not a magnesium that you use for making fire. It's a different kind of magnesium. It's a magnesium element. But you can use other metals. I use lead. I use zinc rods, and they all pull off a voltage. Magnesium seems to give you more bang for your buck. And to show you, it's already getting hard. This is already hard like concrete. But this is salt, so you just add a little water to it and it melts. Alright, this is one I made about 6 months ago. And you can see as the crystals kind of expand, because I had cleaned all this out flush. And the crystals expanding and growing and pushing that. And I guess that's what makes the electricity, is the fact that the crystals push on the different kind of metals and make electricity. I guess this is about 6 months old, maybe a little bit more. Got my little meter right here. Got it on DC. The magnesium is going to be negative. And the copper, because I got this wire connected to the copper, that's going to be positive. The copper is going to produce positive, and this is going to produce negative. So it's already 1.3. In time, as it draws, the crystals will push and push and push, and it draws out. See, this one I just made is I don't know what the voltage is. We can check it though, but it's still cooking. It's need to let's see it, but let's see. It's a volt. 1.5 volts, and it's only been sitting there about 10-15 minutes. As it cools down, the voltage is going to drop. But you also can charge these things too. Watch, you can they hold a pretty good charge. Put positive and negative. Positives on the copper, negatives on the magnesium. And I can put it on here. Put it on about 10-15 seconds. And check it again. It's going to be a little bit higher. See, 1.6. It was 1.5, and that was just for a few seconds. But once you put a load on it, it drops down. Yeah, they got a good voltage, but the amperage is pretty low. So what I do, I'll make like 6 of them, and put 6 of them on some kind of whatever I want to run. And it doesn't increase the voltage; it just increases the amperage. The voltage can still be about 1.5 volts, maybe 2 if you're lucky. But when you add a bunch of them together, it just increases the amperage. But anyway, this is pretty good for about 6 months, 7 months old. And it's been having a load on it for that long. I've been having it run a bunch of LED lights, which I'm about to run somewhere here on this breadboard. This is a Joule Thief circuit. You can Google it. They're pretty simple to make. It's basically just a Joule Thief, which is basically a bunch of copper wires on an iron core. I pulled this one out of a TV. I'm not too sure what it's called, but I'm guessing some kind of relay switch. And this one and this one is separate, and I just connected them together. And I put a transistor on there from them little curlicue bulbs, I don't know what you call them. But if you want to, I could show a video on that, but you know, there's a bunch of it's called a Joule Thief circuit. Turn that off. Alright, run the battery. See, the positive is the copper. It goes over here. Twist it on there. And for people who don't know what a breadboard is, it allows you to run circuits without having to solder anything. So when you're testing stuff, you can already see the light came on. But the light's just there to show me that it's working. You can do more than this light bulb. Let's see. That's gonna be the negative. Alright, let's see what we got here. That's the only thing I found kind of off, because I drill a hole and put a screw in it, but that one's good, but I would wrap a copper wire around it, like these. I can tell after about 6 months it's starting to get corroded a little bit. So maybe in the future I might start drilling holes in them or something. And I've been having like I said, you're not gonna power your house with it, but you can have a flashlight that lights up non-stop for a long time. And you don't have to have a Joule Thief to run it. Just a Joule Thief helps you run it with a weaker battery. I'm gonna keep on putting lights on it until it dies. When it dies, that means you reach the max of its capability and power. Alright, so that's pretty neat. These things are pretty cool. But like I said, you're not gonna power a house with it, but you can power some lights. And it's just something that's, I thought pretty good. They got people who make them, and they got like copper bowls about this size, and they get more of a voltage out of it, more amperage. You're naturally bigger. But a lot of people like to make them small because you can put more of them together and get more of an amp to it, and it pushes the electricity. But just keep experimenting, because it's a new thing, and just keep experimenting and see what happens. Just leave comments on new things that y'all find and discover, and share it with the world.